Section 5.2 deals with integration by substitution. So now integration by substitution allows us to integrate functions that we can't separate into individual terms. It's integrating the chain rule. So recall the chain rule from section 3.4 said that the derivative of f of g of x was equal to f prime of g of x times g prime of x. So what we're doing is we are going to undo this chain rule when we integrate by substitution. So how do we do this? Well, we're going to let u equal one of the functions that we find in our integrand. Usually it's going to be the function that's being raised to a power, the function e is raised to, or the function in the denominator. And we're just going to call that function g of x to give it a name right now. Then we want to find the derivative, or du, which means we need to find the derivative of g of x with respect to x. We use substitution to convert the entire integrand, so the entire integrand in one involving u. Once we've converted it, then we're going to be able to use the rules for integration that we learned in section 5.1 to integrate. We integrate our function, and then finally we replace u with whatever g of x was so that we can get an answer in terms of x. So let's look at example 1 here with these steps. So the first thing I need to do is let u equal one of our functions. And typically, again, it's the one that is being raised to a power, or the function e is raised to, or the function in the denominator. So the function that's being raised to a power is x squared plus 1. It's being raised to the 7th power. So I'm going to let u equal x squared plus 1. Step 2 is find the derivative, find du. So the derivative of u is du, and the derivative of x squared plus 1 is 2x dx. We just took the derivative of an x term, so we're going to write that dx. Step 3 says now use substitution to convert the entire integrand in one involving u. So what we want to do is we want to convert this whole entire thing into something that just has u's, no more x's. Now before I do that, I'm just going to rewrite this integral as x squared plus 1 to the 7th power times 2x dx. Now there's nothing wrong with what I did. I can do that because multiplication is commutative, so the order in which we multiply doesn't matter. But I'm doing this so it makes the substitution just a little easier to see for us. So step 3, we want to substitute everything in terms of u. Well, I know that x squared plus 1 is equal to u. So instead of x squared plus 1, I can write u. It's still being raised to the 7th power. I also know that 2x dx is equal to du. So instead of writing 2x dx, I can write du. So I've just in step 3, I've converted myself into something that's completely in terms of u. So now, step 4, evaluate it using the rules that we learned in section 5.1. Well, this is just the power rule, so my n here is equal to 7. Therefore, this is going to be 1 over 8 u to the 8th power plus c. Finally, step 5 says, now replace u with whatever it was in terms of x. Well, for us, remember, u was equal to x squared plus 1. So my last and final step is to, instead of writing u, write x squared plus 1. So the answer for the integral of 2x times x squared plus 1 to the 7th dx is 1/8 x squared plus 1 to the 8th plus c. So recall in step 1, I tell you that u is typically going to be one of the functions that is being raised to a power, that e is raised to, or the function in the denominator. So we have these, in general, indefinite integral formulas that say if you have a function raised to a power times the derivative times dx, that it just integrates as 1 over n plus 1 f of x to the n plus 1 plus c, as long as n doesn't equal negative 1. Well, this is just another way of saying this is the same as u to the n du. This one e raised to a function times f prime of x dx is going to be e raised to that function plus c. So this is going to be an e to the u du. And this one says if you have the integral of 1 over u du, that it's going to equal that natural log of the absolute value of u plus c. Alright, so let's continue on. Let's look at more problems where we're using substitution. Step 1 says to figure out what you should let u equal. U is typically going to be what is being raised to a power, the function e is raised to, or the function in the denominator. Well, notice that in the denominator I'm being raised to a power, so I'm going to go ahead and say u is going to equal that x cubed plus 2x. Now if u is equal to that x cubed plus 2x, then my derivative du would equal, well, the derivative of x cubed is 3x squared, and the derivative of 2x is 2 times dx. Well, again, I can rewrite this if I really wanted to as the integral of 1 over x cubed plus 2x squared times 3x squared plus 2 dx. This part isn't necessary, but it makes seeing the substitution a lot easier. Therefore, I can write this now as 1 over, recall x cubed plus 2x is equal to u, and that's u squared, and my 3x squared plus 2 times dx is equal to my du. So now I have an integral all in terms of u, and I need to integrate this. Well, remember, when I have u to a power here in the denominator that isn't 1, what I need to do is I need to rewrite this. Therefore, this is the same as u to the negative second du. So here my n is equal to negative 2. If I'm using my power rule to integrate this, I'm going to have 1 over negative 1 u to the negative 1 plus c. And then finally, instead of writing u, I want to put the x's back in. And let's clean this up in the same step. So 1 over negative 1 is negative 1. My u again is my x cubed plus 2x, raising that to the negative first, plus c. So the integral of 3x squared plus 2 over x cubed plus 2x squared dx is that negative 1 times x cubed plus 2x raised to the negative first plus c. Let's do number 3. Now number 3 is tricky because it's got e raised to a function, it's got e raised to the negative x, and it also has something that's being raised to a power. So the question is, which one of these guys is u? Well, the thing is that when you label something as u, you have to be able to take the derivative of it and find it there. So I always tell my students that if you have something like this, you're still going to make your u equal what's being raised to a power. So in this case, I'm going to let my u equal 1 minus e to the negative x. So if u is equal to 1 minus e to the negative x, then du would equal, well, the derivative of 1 is 0, then negative, the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1 dx. If we were to clean that up, well, a negative times a negative is a positive, so that's just e to the negative x dx. And I have an e to the negative x dx. So perfect. This was the best choice for you. This would not have been. So what we want to do now is, and again, we don't need to do this, but it just makes substituting a little easier. So 1 minus e to the negative x raised to the 5th times e to the negative x dx. So then this becomes, well, remember, my 1 minus e to the negative x is equal to my u, and that's being raised to the 5th power, and my e to the negative x dx is my du. So now I'm a function all in terms of u, and I can just integrate this. So I know that this is going to integrate as, well, this is my power rule. Here my n is equal to 5, so I'm going to integrate as 1 over 6 u to the 6th plus c. And finally, get the u out, put x's back in, Therefore, we're looking at 1 over 6 times 1 minus e to the negative x, all of that raised to the 6th power plus c. So the integral of e to the negative x times 1 minus e to the negative x to the 5th dx is equal to 1/6 times 1 minus e to the negative x raised to the 6th plus c. Well, sometimes we actually have to do a little bit more work to get the du to equal exactly what's there in our integral. So for example, here, the thing that's being raised to a power is 5x plus 1. So I would say, okay, well, my u should equal 5x plus 1. But if I take the derivative, du, well, the derivative of 5x plus 1 is 5 dx. Well, notice I don't have a 5 dx. All I have is a dx. So what I want to do is I need to make this match that. Well, how do I make 5 dx become just dx? Well, I can divide both sides by 5. So there's no number in front of du, but we know that there's an implied 1. So then we can say that, all right, well, 1/5 du is equal to dx. So my dx, which is all I have left in my integral, is actually equal to 1/5 du. So if I rewrite this, I have the integral of, recall, 5x plus 1 was my u, so u raised to the 8th power, and my dx is my times 1/5 du. Now, this is probably the last time I'll write it like this. I'm going to skip to this next step in all our future examples. 1/5 is a constant multiplier, and we know that constant multipliers multiply along. So whenever I have a constant multiplier here with my du, what I will always do is I'm going to just factor out that constant multiplier when I'm writing my integral. Well, this is something that I know how to integrate because I'm just using my power rule. Here my n is equal to 8. Therefore, I'm looking at 1/5 times 1/9 u to the 9th plus c. Over here, 1/5 times 1/9 is now 1 over 45. Instead of writing u, I write what u is equal to. So that is your 5x plus 1. All of that raised to the 9th power plus c. So the integral of 5x plus 1 to the 8th dx is 1/45 times 5x plus 1 to the 9th plus c. Let's look at example 5. Here I have e raised to the 2t dt. Now remember, when it's e raised to a function, your u is going to be that function. So in this case, my u is going to equal 2t. Well, if u is equal to 2t and I take the derivative, du would equal, well, the derivative of 2t is 2, and I just took the derivative of t. Well, notice that I don't have a 2 dt. All I have is a dt. So I divide my 2 from both sides. Therefore, I can say that 1/2 du is equal to dt. So if I were to substitute, I end up with e. Remember, 2t is equal to u. So e to the u. And my dt is 1/2. Constant multiplier goes on the outside. Du. So my dt was equal to 1/2 du. Since that's a constant multiplier, I'm always going to place that outside of the integral. Well, I know how to integrate this because the integral of e to the u is my favorite. The integral of e to the u is e to the u plus c. Last and final step is to get rid of the u and put the variable back in. So in this case, I'm looking at 1/2 e to the 2t plus c.